Yeah. So hello and welcome everyone to the day 4 of the course. Today we talk about how to perform a multimodal analysis, multiphysics analysis. Let me just brief about the problem that we will be doing. A quick raise of hands of how many people will do along with me so that I will get an idea. Okay, good. That's good. So I will share my screen. Okay, so what we are going to do is we are going to create a structure like this. Okay, and we're going to launch an electromagnetic plane wave as we have done before. Okay, and this would be an air domain. What we will do extra is that we will add a silicon domain, a lossy domain. This was silicon glass, silica glass, and this domain is a lossy domain. Okay, so because it is a lossy domain, we would actually see the rise in temperature, and because of the rise in temperature, uh, you could actually see some kind of deformation. So we wanted to see this, how to do the coupling of electromagnetics with other physics. Okay, so we'll launch the wave from here, and we'll exit the port from here. Okay, looks good. Any questions on the model setup? Anyone? Okay, so let us get started. So once you open console, you can see over here the model wizard. So it's always best to go with model wizard. Just click on model wizard, and to save the computational time, I will do the 2D simulation. Okay, and then we can go ahead and go to wave wave optics, and choose the same electromagnetic waves frequency domain, and click on add. Okay, I'll wait for a few seconds for you guys to add this. If you have any questions, you can please unmute and ask. Should not be a problem. Okay, so you need to add electromagnetic waves frequency domain, then click on study, and then go ahead and select frequency domain study. So here we will see how to run different kind of studies, because if you see electromagnetics are working in the time scales of nanoseconds, while heat transfer, that is a rise in temperature as well as the change in the deformation, happens in order of seconds or minutes. Okay, so they both work in a different time scales. Okay, so we will try to understand how to do a multi multi study, means multi domain study, means we will run frequency stationary study together. Okay, so just as of now we will just run the electromagnetics. So even if we are doing a multi-physics problem, it is best to start simple first, and then slowly and steadily add more complexity. Okay, then just add frequency domain and click on done. Okay. Yeah. Uh, quick raise of hands to know how many people have were able to do this. Okay, yeah, that's good. If anyone is stuck, just let me know. Okay, as you know that we are going to make geometry in the case of wave optics, and wave optics we deal with order of micrometers or nanometers. Working with in order of meters or kilometers are the purpose of is the purpose of ray optics. Okay, so we go ahead and choose the length unit from meter to nanometers. Okay, and in parameters, you can go ahead and choose name as LDN naught and give 545 nanometers. That is the operating wavelength. Okay, so I hope you were able to add this. The next thing is to make the geometry. As we have said, we will make this geometry. Okay, so how to make this geometry over here? Just right click on the geometry, click on the rectangle, and I will make geometry of 1000 by 2000. Click on build all, and you get a geometry like this. Okay, so I'll wait a few seconds for you guys to add this geometry like this. Okay, I hope you are able, made the geometry. Next thing, we are going to create one small nanorod. Uh, I'm saying it nanorod because it is extending towards infinity, toward the screen and towards you. So how do you make a nanorod? Is just right click on the geometry, make a circle, and make it to be radius of around 50 or maybe 100. Okay, and shift it to 500 and 1000, so it will be in the center. Okay, this is the base position, and base position is through center, means this is the center, and the coordinate of the this circle is 500 comma 1000. This is 500 and this is 1000. Okay, so a quick um, raise of hands if you are able to make this geometry.
And the circle is not in center. It is coming some side.
Yeah, so you just need to change the position. The base should be 500 by 1000. Okay, when you are in the circle, the base position should be 500 by comma 1000. Coordinates of this center should be 500 by 1000.
Sir, the base should be set, keep it in center. Previously it is in corner, like that.
Okay, in this circle, you can put it as center, 500 by 1000. Make sure it is circle, it's not the rectangle.
Okay,
Yeah.
rectangle it is corner, no issue.
Yeah, yeah, that's not a problem. Yeah. Okay, I hope you're able to do this. The next thing is to add the material. So just right click on the material, right click on the material, add material from library, go to built-in air domain, just double click on the air domain. Okay, so air you can see has been assigned to both the domains, the rectangular domain and the central rod as well. Okay, now what I need to do is that I can add the silica glass material. Okay, just double click on the silica glass and assign it to the central domain. You can see, just double click on silica glass. You can just zoom in a little bit so that you can easily select. You need to select the central domain.
Sir, but why we added that air material in that circle also initially?
Yeah, by default, the air material has been assigned to all the domains. Whichever material we add first is assigned to all the domains by default. It's not in your hand. So now, as you have added silica, you can see that this has been now overridden by the silica.
Okay, okay.
So it shows doesn't matter. Also,
Sorry.
if it shows overridden doesn't matter.
It matters, right? Because well, it will not matter for this. Means actually now the domain number two is silica glass. It's no more air. Even though it is in here, but the second domain, that is the red now, has been overridden by the silica glass material properties. It's
Okay.
mentioned over here. Now you can see that currently there are two tick marks over here: refractive index real part and refractive index imaginary part. Now because we are only solving for the electromagnetics problem, only these two material properties are being used. So these two tick mark means these two are the material properties being used. Now because want to model some lossy domain, I will put non-zero imaginary part. I will put 1e minus 6. Okay, so I'm putting the imaginary part to be 1e power minus 6. So it's now lossy. It's no more lossless. Okay. The next thing what we need to do is just right click on electromagnetic waves frequency domain and click on port condition. Apply in the top boundary. Okay. What I want to do is I want to launch an electromagnetic wave, plane wave, oriented in out of plane direction and propagating in minus y direction, means towards bottom. So I use the type of port as periodic, wave excitation as on, This right now I'm using the earlier version of console. So um, my system actually crashed yesterday, so older version. In this 6.1, there will be no S or P polarization. Here we have to manually enter the mode field amplitude. So out of plane would be 1 0 0 1. Okay, if you are using earlier latest version of console, you can use S mode. S mode means out of plane.
So can you please tell the value of imaginary?
Imaginary value is silica glass 1e minus 7 minus 6, 1e minus 6. Can you see?
Sir, in the port mode setting, the polarization is there, defined.
Sorry, come again.
In the port mode setting, there is a polarization that user defined, not shown in your software.
Yeah, you can use S plane as we have done in the first
There
class.
is there is three sections: linear polarization, circular
You use
polarization, and
linear polarization.
okay, that is yes.
Uh,
Then the previous 001 we give, that is not there. There is no
it's the
electrical
same
field.
thing actually. If you put S polarized means it is out of plane, and this is the same as 001.
If we didn't use user defined, we can go for the
No,
electrical
no,
field
don't
same
use the
section.
user defined port. Type of port you're saying?
Port mode setting, port mode
Port
setting,
mode setting. You can use linear polarized and
polarization.
S polarized. If you use user defined, then you can use this one.
Yeah, there is two options, means
Yeah, yeah, yeah,
polarization and input
yeah, yeah. Correct,
quantity. That
correct,
another section.
correct, correct, correct. Okay. Now I have launched my plane wave from the top. I want to have listener port in the bottom. So I just duplicate this port, remove the top boundary, add the new bottom boundary, and make the power to be off, and everything remains the same. So you can see now the arrow is pointing towards down.
Sir, can you repeat?
Yeah, so what I've done, I've duplicate this port. So I'm getting port 2 now, and I've changed wave excitation from on to off.
Okay, sir.
And I've selected the bottom boundary.
Yeah.
I'll wait for a few seconds for you guys to add this.
Sir, do we need to deselect the second one?
Deselect means?
Previously we selected one, and in the port two we need to we selected the other point, but the both are coming in upside arrow. In the second port we have selection of 2 and 3.
No, no, don't choose 2 and 3, just choose 2 only. If 3 is there, remove the 3. Okay, so in port 1 would be only for the top domain, top boundary, and
Okay,
port 2 would be only for the bottom boundary. This is the listener port.
okay. So how to remove, sir?
Just click on it, it will go away. You click left click, it will come again.
Okay, okay, okay. Understood. Yes, sir. Done.
How about others? They are able to add the port conditions. Let me know if you are facing any problem. So what would be the next boundary condition? Can anyone guess?
Exterior.
Yeah,
Periodicity.
yeah, we
Oh,
need to apply periodic conditions. So just right click on the electromagnetic waves frequency domain and click on periodic and apply it to the left and the right because we are using periodic ports. Type of periodicity as fluctuate. K vector for the fluctuate periodicity is from the periodic port.
Sir, in this one there is no coordination system selection.
Sorry.
Coordinate system selection is not
Nah,
there,
don't
and
worry about the coordinate system. This is not required. Coordinate
okay,
system is not required. Don't worry.
is user defined? No, from the video. Okay, sir.
Yeah. So whatever this whatever is it, you keep it. No, no problem. Should
Okay,
not
sir.
be a
Done.
problem. Okay, then you just go to the frequency domain and change this as. Do we have defined LD naught? Yeah, we have defined. So I'll change this to C constant by LD naught. Okay, so I hope you have added that. Now, because we want some more significant losses to be um, um, seen, what we will do is that we will increase the power. Okay, so go to port 1 and you can change the power to around 100 watt per meter. Okay, just so that we can see some significant rise in temperature. So you can actually choose whatever is required. Okay, so I put this 100 watt per meter. Next, you can just go to the mesh and see the mesh how it looks like. That's it. Then just click on compute. So you can. So always when you get the results, just try to see the component of a specific electrical field and try to see the animation as I have been telling all these days. Yeah, so you can see it's propagating nicely. So ideally, you should have removed that silicon domain and directly seen the air domain. Then nicely it is propagating or not. Then you add silica glass domain in the center and then try to see some kind of obstruction. Okay, so how many of you are getting this kind of fields? Z component of electrical field? Okay, so I hope you are getting the Yeah, sorry, I think I lost my connection. Can you hear me now?
Yes, sir.
Okay. Yeah. Yeah. So my question was, why do you think there would be some losses in the central domain? Any guess? Like I'm passing an electromagnetic plane wave, so why there would be some losses? When there are losses, because of which effect?
Absorption.
Yeah. So if it is a conducting material, then there would be some kind of I square R losses. Okay. If it has some finite conductivity, then because of I square R power losses, we can see. So how do I quantify the losses? So just right click on the results, 2D plot group, and I just right click on the 2D plot group again, click on surface.
So can you show your screen?
Oh, sorry. Yeah. Yeah. Can you see my screen?
Yes, sir.
Yes,
Yeah.
sir. Yes.
Yeah. So I will do this again. So just right click on the results, 2D plot group, and right click on the 2D plot group again, and click on surface. And over here, um, I want to see the losses only in the central domain, okay, not anywhere else. Okay, only central domain. So what I will do is that I can right click on the surface, choose selection, and select the central domain only. So actually I can see the losses only in the central domain. Okay, so I'm adding a additional selection on the surface. So if I want to see the losses, how do I see? I just search for losses, and this is the variable ewfd.qe. That is the complete electromagnetic losses. I'll just share with you guys as well over the chat box. And I click on plot. So you can see the losses, which are in order of 10 power 9 watt per meter cube. I'll wait a few seconds for you guys to be able to find this.
So could you please repeat the lost thing?
Means this, how do I search this variable name or this
Uh,
selection?
yes, so that selection, like
Yeah.
how to see that loss.
Yeah, just right click on the surface and add a selection. It would be available over here. When you open selection, it's just like selecting the domain where you want to see that particular variable. I don't want to see everywhere the losses, because this is the only lossy domain. The other domains, the losses would be anyway zero. So I select this domain, left click on this, and then I search for what is the variable of name of the losses. So I just click on replace expression. I just search for loss, and here you can see the losses. So I use the total electromagnetic losses, QE, EWFD.QE. Okay, so I hope you are able to see these losses. Now you know that there are losses. So now I want to know that this losses, can it contribute to rise in the temperature of the nanorod? Okay, so to do that, what I need to do is I need to add the heat transfer physics. How do I add the heat transfer physics? Just go to the physics node over here, add physics. Once you click on add physics, you go to heat transfer interface, heat transfer in solids. Just double click on that. Okay, I will wait for a few seconds for you guys to search
Sir,
for
can you
this.
repeat, please? Sorry, I missed it.
Yeah, just click on go to this physics, add physics, and
Okay.
then you go to heat transfer. And as I want to
Okay.
know the perform the heat transfer on the solid domain, right? I'm
Mm-hmm.
going to use heat transfer in solid. There is no airflow over here, so I don't select heat transfer in fluids or heat transfer in solid and fluids. There is no conjugate heat transfer, right? So this is simple heat transfer using losses in the nanorod.
Okay.
Okay, just double click on the heat transfer in solids.
And then we just select the nano dot, or we select, I
Yeah,
mean, by default,
so
it's
yeah,
both these
by
are.
default it will select both of them. So you
Hmm.
deselect the air domain because you are not interested to
Yeah,
model the air heat flow in the air domain.
right.
Okay, so I hope you have added this physics and selected this nanorod in heat transfer in solid. Now we want to couple the losses which is from electromagnetic waves domain to the heat transfer. So how do we couple it? You just need to go to this multiphysics node. And before coupling, you can see now you can go to the silica domain, silica glass material, and you can see now earlier there were only two tick marks. Okay, so now you can see there are five tick marks. So earlier only refractive index, real and imaginary part were used, but now thermal conductivity, density, heat capacity at constant pressure, all these three are a property of the heat transfer interface. Now those have been also been selected. Okay, so now when I go to this physics node, just right click on the physics so I can do the coupling, and I can say electromagnetic heating. Okay, so now you can see this is the source, and from the electromagnetic waves domain, the losses are being coupled to the heat transfer in solids. Okay, now you go again to the silica glass material. Just see that. Okay, so this fiber anyway there looks good. Yeah. So I hope you are able to add the electromagnetic heating interface, which is a coupling between heat transfer and the electromagnetic wave. Okay, so I hope you have added this electromagnetic heating. Now, what we are going to say is that, as I said, that this both the time scales of electromagnetic and heat transfer interface are different. That is, electromagnetics, it works in the scale of nanoseconds, while the heat transfer works in the time scales of seconds or minutes and even hours it takes to heat up. Okay, so we are going to use some study known as frequency stationary study. So frequency stationary study, when we use frequency domain, would be applied for the electromagnetic heating, and stationary study would be performed for heat transfer in solids. When we talk about stationary study, it's like a steady state analysis. So that at time t equal to infinity, what is the rise in the temperature? As we are doing a steady state analysis, and we are continuously heating up the domain, it could be understood that we are never going to reach equilibrium. Okay, because we are always having the losses, and the losses is kind of heating up and keep on constantly heating up uh, the nanorod at a particular rate. However, if you see, if this nanorod is present in the air, there could be some cooling effect also. The rod is being exerted. Okay, for example, the flow of the air. So this cooling effect is given by convective heat transfer. Okay, convective cooling. So how to add convective cooling is by just right clicking on the heat transfer in solids and click on the heat flux. Okay, and select all boundaries. So now all of these boundaries can be actually can have the convective heat flux. So now we can go to general, instead of general inward heat flux, you can go to convective heat flux and choose heat transfer coefficient of 5. Now based on the geometry and the size, this value actually changes, but 5 is a good number. Even there is one blog from which you can get to know about what values of heat transfer coefficient you need to apply. Okay, but this 5 is a good number. It's fine. Means usually if you are going for a very smaller dimension, so heat transfer coefficient may increase significantly. But as of now, just for purpose of showcasing, I am giving you the value of 5. I'll wait for a few seconds for you guys to add this heat flux boundary condition. Okay, so I hope you have added the heat flux boundary condition. Now you can go to the study over here, add study, and then there's something as frequency stationary. Okay, so select this. You can see this frequency stationary means frequency domain would be done by electromagnetic interface, and stationary would be done by heat transfer interface. Okay, just double click on this frequency stationary, and here you can see what kind of studies that it's going to perform. Here I just need to again go to frequency and write C constant divided by LDA naught, because this LDA naught I have given over here as 545. Okay, so I will wait for a few seconds for you guys to add this frequency stationary study. I hope you were able to add this frequency stationary study. Any questions so far? Any concerns? Okay, so that's it. Just we need to then click on study, to see how these things are going on. Yeah. So the first thing that you can see is again seeing the losses. Are the losses being seen or not? That is the first thing you will see. If the losses are not seen, then there is no meaning in heat transfer. Okay. So it could be inductive losses or resistive losses, any of the losses, but it should be observed. But now you can see that there are finite losses, which makes sense in order of 10 power 9. And then you can see the temperature over here. So now the temperature is rising. By default, the room temperature is 293, but now the temperature is of this nanorod is around 316, okay, Kelvin. So you can see, you can change the temperature unit from here as well. Okay, now it is um, in degrees Celsius. Okay, so how many of you are able to get this result? Are you able to get this losses? Okay, get it. That's great. Now the next thing is, now we have the losses. Now we have to couple this for heat transfer, the heat transfer to the solid mechanics. For example, I want to see how what is the deformation of this silica glass because of the rise in temperature. Okay, there is certain rise in temperature. Because of this, how much is the deformation? So how to add deformation? Just go to the physics, add physics, and you need to go to structural mechanics and solid mechanics. Just double click on solid mechanics. I'll wait for a few seconds for you guys to find this solid mechanics. Okay, so I hope you have able to add this solid mechanics. By default, is as you can see, solid mechanics has been added to both the domains. You actually need to select only on the inner domain. So just deselect the second domain. Okay, so only the central domain has been now selected. Now, because of the rising temperature, there has to be now. If you see, you go to silica glass again, and now if you see earlier, there were only five material properties that were selected. Tick mark was there in front of five. Now you can see there is 1, 2, 3, 4, 5, 6, 7. Two more has now come into the picture. That is Poisson's ratio. Sorry, Poisson's ratio. I think it was there or no? Young's modulus and Poisson's ratio. Yes, these two has come into the picture now. Okay, so it's very important to check whether we are getting the tick mark or not. Now we have to couple the heat transfer to the solid mechanics. So how do we do that? By right clicking on the multiphysics, you get an option of thermal expansion. Okay, so select thermal expansion and select the central domain, and here you can see that it has been coupled from heat transfer to the solid mechanics.
So could you please repeat why we're doing this step? I just missed.
Yeah. So now we have wanted to study because of the rise in temperature, what is the deformation, right? So deformation, if you want to study, you need to do the solid mechanics study, uh, and you need to couple the heat transfer rise in temperature to the solid mechanics. How do we couple that? You couple using the thermal expansion node,
Expansion.
multiphysics node. Okay, this is
Physics.
for multiphysics coupling. How do you couple multiple physics? So for example, electromagnetic
Okay.
heating was used to couple the electromagnetics wave and the heat
Waves to
transfer.
the solid.
Yeah, thermal expansion is used to couple heat transfer with the
Deformation to the.
solid mechanics. Yeah.
Mhm.
So any complicated model that you do, the procedure remains the same. Okay, now you would have added this thermal expansion, and in the solid mechanics now, if you go back, we have to be very sure because it cannot be this um, gold or this silica nanorod cannot be hanging somewhere in air domain, right? So it has to be having some kind of a fixture somewhere or some kind of fixed points, so fixed constraints. So to add this kind of fixed constraints, it will be always there that it has to be um, a few of the points or the boundaries would be fixed. So how do I add that? How do I add that? Just right click on solid mechanics and go to here this option of fixed constraint, that is for boundaries. Okay, what we will do is we can go for more constraint, no sorry, uh, points, and go for fixed constraint. So I'm going to apply a constant on this point. So I select this fixed constant within the points, and I select this point. Okay, so this is very important step before we do the multiphysics analysis. Again, we can actually but that's it, not nothing else is required. That means that this point cannot have a deformation. Even in using the equation, you can see that deformation is equal to 0. Okay, so you can go to the study, add study. Again, you can go for a stationary frequency stationary study, which means that the electromagnetics will perform the frequency domain and heat transfer and solid will perform the stationary study. Okay, yeah, and after the heat expansion, thermal expansion multiphysics node.
Sir, can you
Sir,
repeat the final step, sir? After added to the frequency stationary study, what to do, sir?
But that's it. Just add a frequency stationary study. That's it. Nothing. We don't need to do anything.
so
Oh,
the, no need to change the frequency.
Yeah,
That means
frequency. I am coming to that. Yeah. So now we need to change the frequency. C underscore const divided by LD naught. C by lambda. Okay. So that's it. Just go to study 3 and compute. Okay. So now you're getting some results. So again, first always see the losses. Are you getting some finite losses or not? I can see the losses. Then you can go ahead and see the temperature plot. You see some temperature plot. You can see the temperature plot is in Kelvin. You can also go to the stress plot and you can see this is the von Mises stress. Solid dot Mises is nothing but the von Mises stress, and then I can just, instead of solid dot Mises, I write solid dot disp. Similar of searching displacement, I want to see what is the displacement. So you can see this solid dot disp, and I find out. So you can see this is the deformation. So this is the original boundary, okay, but this is the after deform. After deformation, how the nanorod looks like. So it's actually expanding.
Sir, can you show the last step? Repeat.
Yeah. This in the stress surface one, you need to click over here and just search for displacement.
Sir, how the isothermal condi- the
Sorry,
isothermal thing? Sir, how the isothermal contours, those things
this
do.
is by come by default.
So in my temperature there is no isothermal.
No problem. It's just an additional plot that is coming by default. If you require, you can plot it as well. We are using a different version of COMSOL, so this minor thing might be available, might be different. But are you able to plot the surface plot? Are you able to see this stress plot, some deformation in order of 10
No,
power
sir.
minus 4
No, sir.
nanometer?
No.
What are you seeing?
We think the in structure inside that one, the temperature float is there, na? Sorry,
Mm-hmm.
stress in that one inside a circle, some changes is there. That's all.
Okay. Okay, but how about others? Anyone else getting the deformation?
Yes, sir.
Okay, deformation you're getting, right. So you're able to couple electromagnetics with heat transfer with solid mechanics. Okay. Maybe you can share your screen. I will just go through it.
Hello, hello, sir. Is it visible?
Yeah. Okay. Yeah. So you need to search for solid dot disp, DISP,
Solid dot DSP.
DISP.
Uh, all small.
Yeah, yeah, small.
Yeah, it's coming inside, sir. Not like the structure previously shown.
Yeah, that's fine actually. Yeah, inside only. Mine is also inside only. If you just zoom in, you can see that. This is
Okay.
similar to what I am getting.
Okay. It is zoomed one. I thought it is it's
Uh,
another plot. It's coming
no, no,
inside.
no,
So
no. I have just zoomed it.
okay. Okay. Thank you, sir.
Okay. So you can see that now this deformation can be seen. Okay. Anyone else who is facing any problem, any challenges to get the plot? Okay. So similar to this, we can also run frequency transient analysis. That is, you go to the study. That is, the rise in temperature will happen in time dependent format. So there is a frequency transient, and you can find what is the temperature inside the nanorod in a time dependent analysis. So it's, if you are doing a multiphysics analysis problem using electromagnetics problem, it's ideally to best to start with the frequency stationary, and then you can go ahead with the frequency transient. What I will do is that I will change the time use scales to minutes. I will try to change this frequency to c underscore cons by LDA naught. Okay, and I'll run for 10 minutes with a step of 1 minute. Okay, so it's a range of 0 with a step of 1, until 10 minutes. So I'm going to save my results from 0, 1, 2, 3, 4, like this to 10. Okay, and then I just click on compute. So now you can see this temperature. You click on this, the temperature is 0, or this is 295, this is room temperature, and slowly how it is rising. Okay, so you can see within 1 minute itself it has, so it's actually stabilized or have reached to stability, right? So perhaps we require lesser time scales to see how the temperature is rising.
Sir, what if I'm getting an error saying undefined material property E required by linear elastic material 1?
Yeah, so the first thing that you need to check is solid mechanics. The air domain is not selected. Okay, only the medium
Okay.
central domain is selected. Same goes with the heat transfer in
Yeah,
solid.
center one is selected for solid
Yeah,
mechanics
and
only.
have you selected
Makes sense.
silica glass material or some other material?
Silica glass material too.
Okay, so if you go to this silica glass material properties, can you see
Yeah,
this material
yeah,
properties? Is
yeah.
it empty in the front of
No,
E?
no, it has values. I'm just checking if these are closer to yours. They are exactly the same.
Okay, maybe you can share your
Mm,
screen. I will just look into
okay.
it.
Okay. Can, can you see my screen, sir?
Yeah, it's loading.
Can you see now? I think no, right?
No, I cannot still see it.
Wait.
Yeah,
Okay.
so yeah. By
So
meanwhile, we
can
have.
you can you
Yeah,
see
yeah,
now?
yeah, yeah. I can
Okay.
see you now.
Just a second. Yeah.
So can you close the add study node so it becomes a little bit bigger?
Okay.
Okay. So what is the error? Can you show me?
This one actually for the
Okay, okay,
pri-
okay.
previous
Uh,
undefined material E.
oh, you're doing frequency transient study. In frequency stationary also you're getting error?
Yeah, yeah. I was trying to figure it out, and meanwhile you switched to something else, and I thought that maybe in the next study I will not get it,
Okay.
and I'll resolve it. But again, same error came here as
So
well.
can you go
So
to the frequency stationary study? Just click on frequency stationary study.
study 3.
Yeah.
Okay.
Okay. So now go up. Actually, there seems to be two different solid mechanics physics that you have added. You see,
Solid
solid
mechanics
mechanics
one
and
two.
solid mechanics
Oh,
2.
yeah. Hmm. Why did I do that? Um, so
Yeah,
should I
just delete the
disable
solid.
this
No, disable. Delete it.
later? Yeah.
Yeah. Now you can run that frequency stationary study once more.
Yeah, it says
Yeah, so
undefined.
you just right click on this solver configuration of study 3,
This
not
one?
stationary solver, solver configuration.
This one?
Yeah, right click, delete configuration. Yeah, yes, yes.
Do you wish to remove result?
Yes, yes, yes.
Yeah.
Now go to this solid mechanics again. Sorry, solid
Yeah.
mechanics. Just click on that, left click.
Mm,
Okay, here disable the air domain.
yeah.
Yeah, yeah, correct. Now can you show the fixed constraints once more, fixed constraints.
Fixed constant.
Yeah, right. Okay, makes sense. Now try to run the study 3 frequency stationary again.
Hmm. Yeah, yeah. And the fourth will also run now.
Yeah, can you see this results as in making sense or not? First,
Yeah, yeah, yeah.
Can you repeat the study for?
yeah.
V3 and V8.
Can you see the temperature and the uh, yeah? So temperature is rising, and the if you
Hmm.
go to stress plot, are you able to see some stress being developed? Oh yeah, it's being developed. Yeah, so you can just plot this instead of solid dot
Oh, sorry.
misses. You can go ahead and plot solid dot disp, that is displacement.
Here?
Yeah, solid dot disp.
Mm-hmm. So how do we infer the information from this one, sir? I'm not sure.
Yeah,
Solid dot this. So what do we infer from this plot?
this is the displacement. So you see that the black line that you see is the
Hmm.
original rod, but because of the deformation, it's like just like
Oh, okay, okay, okay.
a railway. Because in summers you see it starts to expand, right?
Yes,
Rail
yes.
tracks. It's like similar to that. So this is the rise in temperature, so it starts to expand. So this is the expansion that you are seeing.
Mm-hmm.
Okay.
Okay.
Yeah.
I think for this one as well, I'll conclude.
Yeah, you can run this part. So I'm just sharing my screen again. So the last part is this of this steady state frequency transient means that frequency domain will run for the electromagnetics and the transient will run for both heat transfer and solid mechanics. Okay. So here you can just add this frequency station transient and click on compute. Okay. Then you can
Sir,
choose. Yeah.
sir, your screen is
Yeah.
low.
Yeah. Hello. Tell me.
Is it audible?
Yes.
Okay. The for mine, the system, the screen is stuck, so it is not visible.
Okay. Are others able to see my screen?
Yes, sir.
Okay.
Yes, sir.
Okay. Okay. So that's what you can actually do. So running a time-dependent electromagnetics problem is very difficult because it's very time-consuming. So if you're doing a physics, multi-physics analysis, it's always good to have uh, uh, do use this kind of studies. So there are a few examples which are actually dealing with this kind of studies. You can also go through that. For example, um, we have with us, if you go to comsol.com,
Ron misses stress. Sorry.
so frequency stationary So frequency stationary EWFT interface.
Hello, sir. I
Yeah,
just lost the connection. So can you repeat the study for, sir? I did.
yeah. Study for is just the same thing. Just add the study, add study, and then go and click on frequency transient. Okay, and then choose what time scale you want to work with, and here C constant by LDA naught. Okay, and then click on compute. You would be able to run this model. Okay, so that's what I wanted to cover in today's session.
Yes.
Yeah, so if you have any other questions, for example, Sahana has a question: can we use a single study node for multiphysics analysis? Yes, single study node also you can use, but it's always better to do. It is always better to uh, simplify a complex problem. For example, if you're doing a multiphysics problem, it's very challenging. So best is if you can uh, divide a complicated problem into small parts. Okay, so for example, if you have 3 4 physics, you solve for one physics first, see the results are making sense, then slowly and steadily you add more and more physics. Okay. Yeah, Abdul has a question. Is there a way to calculate eigenfrequency limited to a specific wavelength range, such as 550 to 650 nanometers, and extract 30 modes within that range? Yeah, that should be possible. Means in eigenfrequency studies, there is a range also you can mention. So there are different kinds of studies in eigenfrequencies. So if you see here, so here eigenfrequency search method around shift. So here you can mention the larger real part and the larger smaller part. Okay, so this helps you to identify what is the range in which you want to search. So here also you can see even region you can mention. Maybe this you can keep it automatic, and then you can see this region, and over here you can mention what is the smallest real part and largest real part. Okay, imaginary part better not to play around with, but the real part and how many number of search you want to do, that you can actually mention. Okay, I hope that answers your question. So next question is how how can confirm the results we got after computing all the multiples is correct or not? Means the way to confirm, we cannot confirm per se unless until you actually do these um, experimental results and confirm, validate. But the way to know whether it's on the correct path or not is to see, as what I have said, S parameters, scattering parameters, the transmittance plus reflectance. Try to see if it is making sense or not. Okay, just try to model the error domain first, and then try to see whether you're able to see the electromagnetic plane wave or a laser Gaussian uh, wave to propagate. Is it propagating or not? So all these things you can actually check. Okay, this is a way to kind of know that you're in correct way or not. but there's no way of saying that the simulation is correct or not. Okay, so that actually depends on us, because all the material properties is in our hand, geometry is in our hand, so all the things are in our hand, right? So the simulation will do whatever we are doing, right? So it actually depends on us to set up the model very correctly, with the closest the closest uh, protocol as what actually you can see in the actual experimental protocol. Okay, in experimental setup should be as similar to what we are actually doing over here. Yeah, so Sahana has one more question, as can we use temperature dependent material properties in multiphysics simulation? Yes, definitely you can use. So you can use temperature dependent means maybe expansion, thermal expansion coefficient is a function of the temperature. Okay, so you can either you can see if that material property is available in COMSOL library, or you can also import a interpolation function. Okay, any function you can bring, or any table you can import using interpolation function, and then you can call that in the material property. So Krishna Bhi has a question, as can you explain how the physics of SPR sensor selected, or otherwise is there documents related to it? So surface plasmon resonance, I think I discussed with you yesterday of having that prism uh, gold substrate example model was there yesterday. We discussed the Kreshman configuration. So I think that is the best way to learn the SPR resonance. I'm not sure if there are specific sensors. Yeah, so this is the one of the example. Okay, and there would be also many papers. If you wish to search, you can also search in the papers and research. You will see a lot of actually work showing over here. So here you can SPR sensor. There will be a lot of work that people have already done. Okay, so you can see how they have actually done. But this is a very good example model. If you're interested, you can go through this. Okay, I'm sharing with you here this one as well as this one. Okay, so any more questions? Okay, so if there are no more questions, then we can meet at 5 o'clock today to have one-on-one discussion. Okay, thank you. Hello and welcome everyone for the one-on-one session. Let me know if you have any questions or query.
Hello, sir. Yesterday we have seen the electric field enhancement. What is this unit? Basically, it is E by EZ or E by E0 square, sir.
Actually, electric enhancement is unitless. Okay, so
It is,
you
sir.
divide by the original intensity square of the original intensity square. So actually, if you see in papers, they report it unitless
Yes, sir.
enhancement.
So this is basically E by E0 square, sir, right?
Yeah, it's square, but it's divided by the original electrical
Okay,
field.
divided
So
original.
original is
Okay,
one,
sir.
for example,
Okay,
one
okay, sir.
volt per meter. So it's a square of that one. So it becomes unitless.
Yes, yes, yes. Thank you, sir.
So tomorrow at the end of the session, we will also have a self assessment quiz at the end of the session, quickly for around half an hour or so. This is just to understand whether you it's a self assessment, so whether you are able to understand the concepts or not. So on those lines, okay, the questions would be around 15 to 20 questions, and it will be a Google form that will be shared, and from there you can attend it. Uh, it will be the end of the first session tomorrow. Okay. Okay, let's wait for a couple of minutes more. Let me know if you have any questions or doubt to discuss. Else we'll dissolve the session. Yeah, so I think Ria has a question as to document related meta surface absorber. So you are interested to make some kind of filters, Ria? Meta surface means some kind of filter characteristic are you looking for? You can unmute yourself and let us know.
Sir, is there any possible to get the extinction spectra of two gold particle, like any arbitrary shape of gold particle, sir?
You what do you want to evaluate?
Actually, extinction spectra, sir. Like I want to guess how the extinction spectra, like say absorption spectra, how it will be look like for any arbitrary shape of gold particle, sir.
Yeah, you can do that. So there is an example, as I discussed yesterday, scatterer on substrate. Okay, so that is the best example to find extinction coefficient. You're talking about
Okay.
exchange coefficient, right?
Yes, sir.
Yeah. So that scatter
Extinction
on
coefficient
substrate.
in x-axis, sir, it will be like wavelength versus extinction
Yeah. So
coefficient.
you just do a 1D plot, you plot, and then that variable you can use it in 1D plot.
Okay, sir.
So just to plot 1D plot group,
Hmm.
and you can plot a global plot because that absorption coefficient is a global variable. Okay.
Yes, sir.
And then in x-axis you can use wavelength, for example, and in y-axis you can call that integration, double integration on the surface, whatever is the variable, because exchange coefficient is nothing but equal to summation of absorption coefficient as well as scattering coefficient, I
Scattering
guess, right?
coefficient.
Yeah, so you can just extinction coefficient, so that you can just add both of them and you can do it. I guess that should work.
Okay, sir.
Yeah, so meta surface for sensing, the best example is always this frequency selective surface, and other is plasmonic wire grating. So these are the two good examples. I will just share my screen. So this is frequency selective surface. So metamaterials is a very broad terminology of saying you are making your own material properties based on your own material dimensions and structures and all those things, right? So there is kind of very broad field, uh, but this frequency relative surface is one of the best example that I can find out for showing metamaterials. Okay. One more example that comes to my mind is plasmonic wire grating. This is also very much similar example uh, in 2D, but the frequency related surface is in 3D, so it actually works very well. Okay, so you can go through these examples as well. And we have to say that meta surface absorber. So that frequency related surface is kind of filter. So it could also work as an absorber for a certain range. So it depends on the material properties whether it actually works as a filter or an absorber. Okay, so you can change the material properties and make it work as an absorber. More important part would be it would be a um, um, function dependent property. Material property means it would be a wavelength dependent refractive index that you have to make sure that you are account for. Okay, I hope that helps, Ria. Okay, next question is photo-induced stress in materials. Uh, the closest example that comes to my mind is optical stress model. So in this case, because of the stress, that is it's the opposite thing what you are saying here. It is the because of external stress, there is a change in mode of propagation inside an optical fiber. Okay. So what are the stress optical coupling between stress and optical effects? You can actually go through this example model. Okay. It could be also the other way around. Okay. We'll share you the screen, share this model file. You can go through this. Ria has another question. How can I take the material property? For example, I want to take graphene as dielectric in terahertz. How can I take the property of that? So for modeling graphene, I think Andrew had written something back way back. Andrew, graphene modeling, and there's a series of blog modeling graphene in high frequency electromagnetics. If you see graphene metamaterial, perfect absorber. So you can also go through this model file. Okay. So in this it would be in terahertz. You see graphene based terahertz metamaterial absorber. That's exactly what we were looking for. I hope so. And this is a blog written for modeling graphene for high frequency electromagnetics. So this also you can go through. Okay. So a lot of work has been done in graphene. Even this block, I think, is also interesting. Whether you model graphene as 2D or 3D. Okay. So this also you can. Yeah. So I'm seeing a question here, that's how to break the symmetry. I don't understand the question as to with what context are you speaking about? Like what symmetry are you talking about? You can unmute yourself and speak as well if you have a mic. How to break the symmetry for tunability? I mean, I don't know. I've not worked on modeling graphene or absorber, so maybe it doesn't. I'm not able to get what context are you speaking. Maybe you can share me some references. I can quickly go through that tomorrow one-on-one session, and then I can help you to understand. Or you can share your screen and share. You can show me what you are speaking about. Maybe I can have a better understanding. Okay, that's good. Happy Guru Purnima. Looks good. So any more questions? If we don't have any questions, then we'll dissolve the session. Okay, we have questions. Okay, so sir, during laser material interaction study, we can visualize the heat transfer mechanism, but if there any material ablation and plasma formation, can we visualize it and study the evolution of plasma? I may not be the correct person to answer this because I've not worked on plasmas and in-depth analysis on ablation. Yeah, so yeah. But if laser material interaction is possible, I've seen some models as a heat transfer interface. So that is the only thing, but I'm not sure I can comment on the plasma evaluation of plasma. Sorry. Yeah. Okay. Any more questions? You can also unmute yourself and ask the questions. Okay, looks good. So thank you very much for the day 4 session, and we'll see you around tomorrow. The last day we talk about ray optics. In the ray optics, we actually talk about how can you model light as rays, that is photons, and with which you don't need to worry about the mesh anymore. Right now, we have been always been worrying about the mesh. So dimensions we are putting in the order of micrometers, nanometers. But in ray optics, as you will see, we're free to use modeling domains in order of centimeters, meters, even kilometers. Okay, that's good. Thank you. Take care. Bye bye.